Hello. Welcome back to our class. Today we're going to be switching modes out of botany and into chemistry. And today we'll be covering the chemistry of plant molecules. In this third module, uh, covering chemistry, you should know how we can name plant molecules and how they behave at the sort of structural level. And then also, how can we determine how much of a change happens? So whether that's a reaction, um, vaporization, or transfer through from one sort of holding agent to another. So today, our goal is to understand how we name plant molecules and a basic set of how they behave. Right, so we'll talk about how we can depict organic molecules, how we can name organic molecules, what the categories are of plant molecules, and which parts of these are fragile and or lead to polarity. So, um, the first question to think about is why does chemistry matter, right? So we've talked about these different plants before. We've got mint, lavender, oranges, and clove buds. And we've said that all of these contain essential oils. And yet they smell different and they behave different during extraction. And why this is occurring is because they're fundamentally different down at the atomic level. So the molecules that are giving rise to these scents are, of course, made from atoms, right? And so we can take different atoms that are going to come from the periodic table of elements, and these atoms are going to bind together to form molecules. So in this case, if we have one oxygen atom and two hydrogen atoms, it forms H2O, um, where the subscript, of course, tells us uh, how many atoms of each element type are present. For our discussion today in natural products in general, the key elements are hydrogen, carbon, and oxygen. So I've highlighted these in red. And then you will also see today we'll talk about nitrogen, but not we will not talk about this, but in general, you may also run across things like phosphorus and sulfur. But today we're going to be focusing mostly on hydrogen up here and carbon, nitrogen, and oxygen. So our atom contains three components. Our nucleus, which consists of protons and neutrons, and our electron cloud that surrounds it, which contains electrons. The nucleus has neutrally charged neutrons and positively charged protons, and the electrons sit in these shells outside of the nucleus. Our atomic number that we saw in the periodic table comes from how many protons exist. So this is what leads to a difference between, say, hydrogen and carbon, right? There's one proton versus six protons. The mass comes from a combination of the protons and the neutrons, and then charge on these atoms arise from differences in the number of protons and electrons. There are three major types of intramolecular bonds or bonds within a molecule: covalent, ionic, and metallic, and three major bonding intermolecular binding types, so bonds that are happening between molecules, and these are hydrogen bonding, dipole bonding, and dispersion bonding. We'll go through covalent and ionic intramolecular bonds as these are what exist mostly for the species that we are going to be talking about, and then we'll talk about the intermolecular bonds. So a covalent bond is a bond between two atoms. So say this carbon atom represented as a C and this hydrogen atom represented as an H. due to the sharing of electrons. So in this diagram, we have a red dot, which is representing an electron coming from hydrogen, and a blue dot representing an electron coming from carbon. We sort of say that these are being shared between this hydrogen and this carbon. So we can have one pair of sharing electrons, and so this would be considered a single bond. We can have two pairs of shared electrons, which we call a double bond, and we could have three pairs of shared electrons, which we would call a triple bond. So even though this molecule has four um, bonds or four sets of paired electrons, they're only single bonds because between each pair of atoms, there's at most one shared pair. Ionic bonds act differently. This is where we have electron transfer from some sort of atom. So say maybe this atom fully donates its electron to B, and instead of sharing, we end up with a positively charged atom, A, which we can call a cation, and a negatively charged atom B, which we call a anion. And, just like we can say, positive and negative attract, so these things are going to be stuck together. In general, that sharing, ionic and covalent bonds aren't, 100% pure. There's some ionic character to covalent bonds. And so we can represent that um, in this notation looking at water, where we say that this, even though we have a single line between these two letters representing atoms, this single line represents a single covalent bond. But because oxygen has a lot more protons than hydrogen, which only has one, that sharing is uneven, and we get what we would say is some ionic character in this covalent bond. So this hydrogen is left partially positive, and this oxygen is left partially negative. When we have this special case of a proton or a hydrogen attached to an oxygen, right, we get this strong polarization of the covalent bond. And then we are left with, this negatively charged oxygen and this positively charged proton. And so these form a strong intermolecular bond between the negatively charged oxygen and the positively charged proton. When this occurs, we call this a hydrogen bond because it's happening between this hydrogen and this partially negative species. And so these hydrogen bonding um, are relatively strong because this, just like this intramolecular bond, is partially covalent, partially ionic. This interbond is got a small bit of covalent character, and so it forms quite a strong interaction. And these can only form when we have our proton attached to an oxygen, fluorine, or nitrogen. These are the species that are going to pull the electrons in that covalent bond strongly enough to form a really strong, strongly polarized covalent bond, and then those same atoms on another molecule. So this is why water, even though it's relatively small, has a high boiling point. It really wants to stick together because of this hydrogen bonding that occurs between the two molecules. Similarly, if we have partially charged species, but there are no protons attached, we still have interactions between the slightly negative and the slightly positive atoms in a molecule. And so we can call this dipole bonds. So in general, we want cases where these dipoles line up. and we have attraction between these negatively charged and positively charged ions between, sorry, partially negative and partially charged, positively charged atoms in two different molecules. We get attraction. But this bond, intermolecular bond, is significantly weaker than a hydrogen bond. All right, the last type of bonding that we're going to talk about, intermolecular bond, is dispersion forces. So as these electrons are zipping around, um, in over the course of time, they can randomly move to, say, one side of a molecule, leaving that side of a molecule partially negative and another side partially positive. And if this happens sort of at the same time between two different molecules, we end up with a partially positive side, a partially negative side, and those are going to attract through electrostatics, right? So opposite charges attracting. Okay, now that we have an understanding of how things can bond, I want to start talking about the molecules which we are interested in. We're going to be interested in a class of molecules called organic molecules. These are molecules which contain carbon. All right, so just think organic means carbon. Within this large category of organic molecules, we have hydrocarbons, which is a subset. And these are molecules that only contain hydrogen and carbon. So I want to consider two different formulas, or one formula, right? C2H6O, and bring to the point as an exemplar that just a formula, so how many carbons, hydrogens, and oxygens exist in a molecule is insufficient to describe its behavior or understand how that molecule is arranged. So we can take these same uh, nine atoms and we can arrange them very differently. Here on the right, I'm showing ethanol. So here we have a single line denoting a covalent bond between this hydrogen and this carbon. Um, Same thing here, 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 etc. And this is structured in such a way that one carbon has three hydrogens. The second carbon has two hydrogens. And then we have the oxygen and then finally a hydrogen. This is going to behave very differently than this structure, methyl ether, which is shown at the bottom. Just like this structure at the top, there's two carbons and six hydrogens and one oxygen. But um, the oxygen is bonded to these two carbons rather than to one carbon and one hydrogen like it was in ethanol. Down here, we've written out the three hydrogens grouped together rather than in this form for ethanol, just for visual clarity. Okay, so even though these two molecules have the same formula, they have very different very different behaviors. Okay, so we can see over here this ethanol is going to form uh, is capable of forming hydrogen bonds, while the dimethyl ether is going to have to rely on weaker dipolar bonds. So they're going to have different degrees of vaporization, and then the chemistry itself is going to be quite different because um, you know this oxygen is bound to carbons rather than a hydrogen. All right, so let's talk a little bit about hydrocarbons. So here's an example of a natural product hydrocarbon, limonene, which we've experienced before. So overall, I'm going to show over the course of the next slides different types of compounds, and it's going to be formatted like this slide, where I'm going to show you the chemical structure and then give some information over here. So limonene has this group up here, this carbon with three hydrogens. It's got this carbon with three hydrogens down here. We've got this ring of carbons attached. And then when we have these rings of carbon attached, we often don't write out the hydrogens once again for clarity, but there are hydrogens sitting on each of these carbons. And every time I have a change in direction of a straight line, that's representative of a single carbon atom. Um, you will never see, have an assumption that an oxygen or nitrogen sits there. This is only this kink. Um, if nothing is written, specifically represents a carbon. So there's a carbon sitting here, 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 and here, even though they aren't explicitly written down. So our hydrocarbons contain only hydrogen and carbon. They're nonpolar. There's the sharing of the electrons between carbon and hydrogen is pretty even, so we don't have a large localization of charge. Because of this, these molecules do not interact very favorably with polar compounds or water. And so we call it hydrophobic. It's, like if you take oil and water, you put them together, the oil separates. That's because it's hydrophobic. It doesn't want to interact with the water. These hydrocarbons are not going to want to interact with water. Um, because of if we look at this, there's relatively weak interactions, right? These interact only through dispersion forces. Um, so they're highly volatile. And so this makes them good for steam distillation and use in extractions via nonpolar solvents. Some of these hydrocarbons are dominant components in many essential oils. And they differ, of course, in the actual structure. So there's a few key points that I also want to point out in our limonene example. The first being the presence of these two lines, right? So all of these lines that we've talked about so far represent a single bond. When I have two lines, that means that this carbon and this carbon are sharing four electrons total rather than just two in a single bond. I also want to comment on the name. So limonene, at the end of this, the ENE indicates that this structure has at least one double bond. And so here, if we look, we can see that there are actually two double bonds. But when you see anything with an "ene" at the end, there's a double bond present. And so we can look at other different names. And so hydrocarbons that end in "ane," A-N-E, have only single bonds. When a double bond is present, it gets this suffix "ene," and if a triple bond is present, it gets "eine." And so we can name hydrocarbons or simple hydrocarbons using combinations of prefixes and suffixes. So if I have only one carbon, it gets the name meth, two carbons eth, three carbons prop, four carbons bute, five carbons pent, six carbons hex, and eight carbons oct. And then we combine it with these suffixes, ein, een, and ein, that tell us how those carbons are connected. So if I have hexane, that means that I have six carbons that are connected only via double bonds. If I have ethylene, ethene, that means that I have two carbons because of the eth, and those carbons have a double bond between them. If I have octane, right, eight carbons, um, singly connected. I could also have ethyne, where we would have, or propyne, butyne, if there is a triple bond in here. And so we can denote this with a single line, two lines, or three lines connecting the different carbons. Okay, so in addition to having sort of these chains, we can have rings, which are cycles of carbon atoms. So here is a hexane, right? So over here we have only single bonds between the carbons. Here I've drawn out the hydrogens so you can see them. And then this is what the structure looks like in three dimensions. The black atoms are carbons. It forms what we would sort of consider a chair-like structure. We can see, maybe here's where you sit and the backrest, and then some decoration. And then we've got these hydrogen atoms which are sitting on the outside. So when we form a circle, we add cyclo in front. So this would be cyclohexane. One of the molecule or types of molecules that we see over and over and over again in natural products are this type of molecule called benzene. And in benzene, here's everything drawn out again in two different ways. Rather than having a single bond between each carbon, there is a alternating single, double, single, double, single, double bonds. We can represent it this way, or we can represent it like this on the right-hand side, where we draw single bonds and then a circle amongst them. This indicates that we have an aromatic structure. An aromatic in chemistry terms literally means that we have this alternating pattern of single and double bonds where electrons are shared between all of the carbons at the same time. Right? And so this molecule, this benzene molecule, has six carbons, six hydrogens, and it's flat, unlike cyclohexane, which also has six carbons in a ring, but has 12 hydrogens, and it has this bent structure. For most of the molecules that we're interested in, or for many molecules that we're interested in, we don't have just purely hydrocarbons. One of these hydrogens have been removed and replaced with some other set of atoms. We call these substitutional groups or functional groups. They're called functional groups because it changes how the molecules behave. How the molecules behave in general. We can write these functional groups in what we call R notation, where R represents some sort of molecule and then any generic molecule. And then we can say that that generic molecule is attached to an OH group. And so we're moving from benzene to phenol. So that brings us to our first type of molecule, molecular class with a functional group, and we'll call these alcohols. So an alcohol is any organic molecule which contains an OH moiety or an OH group. And so we can represent this as ROH. So here we have menthol, and it's got this OH group. Next to it, I've shown linalool, which also has an OH group, but in a different location. The key thing with an alcohol is it has this OH moiety. Anytime we have an alcohol, it gets an OL at the end. OL means it's an alcohol. These molecules are going to contain hydrogen, carbon, and oxygen, right? And it must have this OH group. They're significantly more polar than the hydrocarbons, and they can be hydrophilic, meaning they do like water, or hydrophobic. So think ethanol, or what you normally think of as alcohol, that you can could drink. That is hydrophilic. It can mix with water, um, and so it can mix with water because these OH groups can form hydrogen bonds with the water molecules and each other. In general, these are pretty good in steam distillation and extraction from polar and nonpolar solvents. And, as we'll get used to, like dissolves like, so it will dissolve best in other alcohols, which have combinations of OH groups and so polar OH groups, which are available to hydrogen bond, and nonpolar backbones. The second category is a ketone. And so this is going to look similar to a alcohol in that there's an oxygen, but this time the oxygen forms a double bond with a carbon, and it does not have that oxygen is not bound to a hydrogen. So if we think about this, we have an R connected to a C double bonded to an oxygen, right? So this molecule is called menthone. So when we have one, this means we have a ketone, right? So this generally is moderately polar, can be hydrophobic or hydrophilic depending on how large this backbone is. It's generally more polar than our hydrocarbons, but is still volatile enough that we can undergo distillation. Aldehydes are going to be similar to ketones in that they have this uh, O um, O double bonded to a carbon, but it must be the terminal carbon. This is going to change how reactive these are because being at the end, these bonds are open to attack by other chemicals, which could undergo a chemical reaction. So the key thing in differentiating between a ketone and an aldehyde is the aldehydes have that uh, oxygen carbon double bond at the end of the molecule. And so here we can see this in cinnamaldehyde and citral. So we can either write this out and say cinnamaldehyde, or we can write citral, and that al is going to indicate that it's an aldehyde. So these are moderately polar and can be hydrophilic and are generally fragrant. So this is going to be a lot of things that are really we can our noses pick up on. But because, like I said earlier, that we've got this oxygen carbon double bond at the edge of the molecule, it really leads to these being readily attacked by other molecules. If you're interested in the chemistry and why in depth, I highly recommend taking an organic chemistry class, and you'll spend, 2 semesters really understanding why this is much more fragile than ketones. But the key thing to know is this is at the edge, more fragile, more fragrant. Okay, so now we're going to move into some combinations. So I want to bring in phenols. So phenols are an alcohol where it's the alcohol group is on the benzene ring, right? So here we have our benzene ring, and then attached to that is our OH group, and this we call a phenol. And an example is thymol. Again, this has the all at the end because it's an alcohol. we have to have, it's going to contain our HC and O. It's got to contain this phenol molecule. It generally is moderately polar. Um, it's has both the aromatic and the alcohol groups. Sorry about this. This should be at least one OH group. These are generally strongly biologically active and can be difficult to separate because they dissolve so well. And these phenols are often have strong antimicrobial activities. Next, we'll talk about carboxylic acids and our acids groups. So here I'm showing an example of rosmarinic acid, which you can see this carboxylic acid group right here. So here we once again have a oxygen double bonded to a carbon, and that same carbon has an alcohol group. What's special about this configuration is that the hydrogen can leave this oxygen. It can dissociate and leave this as a negative group. So this is considered an acid. This is generally found. This is generally very polar because we can form ions or right our anionic form when this hydrogen leaves. It's often found as its conjugate base where this proton has, or this proton, this hydrogen has left, and it's usually very difficult to remove via evaporation because it does readily form uh, ions which do not volatilize. Additionally, because it is highly polar, this is generally not good for removal from in nonpolar solvents. Okay, so our next group is going to be ethers. Um, and these are groups which have an oxygen which connect two different carbons. So we have R, a single bond to an oxygen, which is single bonded to another functional group, and that functional group has to be a carbon. Okay, so these are generally low polarity, only slightly hydrophilic. They really want to be in those organic solvents, and they're generally highly volatile. Look that there's no formation of or possibility of forming hydrogen bonds. It must rely on either dipolar bonds, which are going to arise out of this oxygen being slightly negatively charged, or this backbone London forces, dispersion forces. And so here we're showing um, cineole, or also called eucalyptol, or sorry, cineole, and this ol is meaning ether. It can also be written as methyl ether or dimethyl ether. Um, you'll see that written out that way as well. So an ester is uh, contains both a ketone group and an ether group right next to each other. So we have this ketone, right? So a non-terminal oxygen double bonded to a carbon, and that same carbon is connected to a oxygen, which is connected to another um, uh, carbon group. So we have to have this ROC double bond OR set. And so this is generally moderately polar and can dissolve relatively easily. These generally have strong floral aromas, But these bonds, these bonding groups here are generally fragile, and so we can end up getting breakages at this juncture or this juncture. And this is an example, linoleal acetate. All right, so that's going to cover our basic nomenclature of organic chemistry. I want to talk about some additional groups of materials which are important for us and how we think about extraction of fragrances and various compounds. And so these are terpenes, terpenoids, phenylpropanoids, flavonoids, and alkaloids. So let's start with terpenes. So a terpene is going to be our basic or one of the basic hydrocarbon skeletons used by biological um, cells for production of various compounds. So all of these terpenes are combinations of isoprene. And this is isoprene right here. It's got this four carbon chain where on one of the carbons we have a hydrogen and on the other carbon we have a methyl group, right? So methyl meaning one carbon. And why this is very useful is because these double bonds can react with other double bonds to form a chain of single bonds. All of these terpenes have this formula C5H8. In general, we find these materials uh, in what are called monoterpenes, where there are two isoprene units. So this gives us 10 carbons and 16 hydrogens. And as an example, we have myrcene. We can have sesquiterpenes, which have three isoprene units, 15 carbons. And so an example of this is shown here, humulene. And so this is what gives hops its distinct smell and flavor. And then we can also have diterpenes, which have four isoprene units. Right? And so here's an example of this phytol. So you can see that even though we have quite different structures, we can have rings, we can have lots of double bonds or relatively few double bonds. These combinations of isoprene units which have been combined together. So they're highly nonpolar, hydrophobic, um, as you would guess, because there's no oxygens or nitrogens around to form strong bonds. And these often form major components of essential oils. Um, and these tend to be highly volatile because there's weak intermolecular bonds. And this makes them capable or highly amenable for extraction in steam distillation or non-polar solvent extraction. In general, we can associate these pure terpenes with citrus, pine, and hops aromas and flavors. Terpenoids are the extension of terpenes. So an oid, when we have an oid at the end, this is going to indicate that it's some derivative of what comes front. So terpenoid means a derivative of a terpene. And so here we can see structures. If we do the count, we're going to see again combinations of 10, 15, or 20 carbon atoms in general. And so these have usually been functionalized with oxygen and or nitrogen. They're more polar than the terpenes, because of the presence of these OH groups, right? And so these OH groups can form alcohols, they can be ketones, they can form more complex sets where we have combinations of ethers and alcohols. So right, so the key thing is their terpenes, which with a modification, right? And so these tend to be more polar and more biologically active than just our simple terpenes, right? So we can think about uh, these terpenes and terpenoids. Here's an example of three uh, terpenes and terpenoids: limonene, carvone, and carval, which are differing really in what's happening on a single carbon, right? Whether there's a hydrogen, an oxygen, or an OH group, right? And so the limonene is going to have a citrusy flavor. Carvonone is mild, uh, sweet, and has that like green, vegetable taste versus Carvalhal is going to be sharp, minty, herbal, and spicy, right? All just changed based on this single substitution. Okay, so if we sort of compare terpenes on the left, we have an array of different terpene or terpenoids, limonene, linalool, menthol, cineole, where only the first one is a true terpene and the others are terpenoids. And their functional groups can differ, right? So within the terpenoids, we can have alcohols and ethers, and uh, this has distinct consequences for how we're going to extract them, right? So limonene is very nonpolar, highly volatile, versus linalool, which is more polar but still volatile. We go down to menthol, which is less volatile and has stronger interactions with each other, so less easily distilled. And then when we go down to our cineole, uh, which is only which is moderately polar, but weakly binding, which can be relatively easily distilled. Right. So even though these terpenes and terpenoids share the same backbone, those functional groups are going to dramatically change its behavior and how we think about extracting them, as well as what we experience when we either smell them, taste them, put them on our skin, etc. So the next set of compounds that we're going to encounter are phenylpropanoids. So these are the compounds that we'll see in spices often, such as vanilla, clove, and cinnamon. So these are going to contain two specific groups. So it has to contain this phenyl ring, so this benzene ring, and an oxygen containing functional group. So in this example, there's a carboxylic acid, right? So two things, oxygen chain or oxygen group and a phenol, so a benzene ring. These tend to be moderately polar, moderately hydrophilic, and like I said, these are responsible for the experiences we get with a lot of spices. Um, they're generally biologically active, but are less volatile than the terpenes. Um, and we generally extract them using ethanols and ethanols or other alcohols and organic solvents. We also have an extension of these, which we'll call flavonoids. Here's the quintessential compound uh, flavone. And the key thing in flavonoids are that we have multiple aromatic rings. We have, in this case, one, two um, benzene rings, and the presence of oxygen functional groups. We've got our ketone sitting right here. And so we can continue to decorate this with various other um, uh, functionalities. So here's quercetin, um, which is the same flavone, just with alcohol groups around the ring. These are generally moderate to highly polar, meaning they're generally moderate to highly hydrophilic. These often are in plants. They're often used as pigments and antioxidants. Usually found in leaves, flowers, fruits, and teas. They're generally non-volatile. If we look at this structure, there's lots of these groups um, with which to form bonds. And so therefore we generally don't see them in, distillates. And we generally have to extract them with water, alcohols, or water alcohol mixes. Oops, sorry. Our last category is uh, alkaloids. And so these are organic compounds that are going to contain at least one nitrogen atom, where that nitrogen atom is sitting within a cyclic ring. So here we have three examples. Here's a nitrogen sitting in the ring, a nitrogen sitting in the ring in nicotine, quinoline, and caffeine. Right. So these generally are moderate to highly polar. We've got a lot of these nitrogens sitting around. Um, these are usually very biologically active and therefore are used a lot in as basis for pharmaceuticals and stimulants. So think caffeine, uh, and so they're psychoactives. Morphine is going to morphine, caffeine, nicotine, right? These are all alkaloids. They've got these nitrogen containing rings. Think psychoactive compounds. Because of this, uh, we're thinking of extraction in water or another polar solvent. All right. Now that we've talked about different types of molecules, I wanted to go um, quickly through uh, how we can think about the stability and polarizable ability of these molecules. So first, let's talk about functional groups and fragility. And everything that I'm about to say is general, right? Not every um, example is going to follow exactly this ordering, but this is the trend. On the left, I've got things that are generally considered generally highly stable, so non-reactive. They're going to undergo processes and retain their molecular structure. And on the right, we have things that tend to be more fragile. They're more likely, they're more reactive. They're more likely to break down and have bonds cleave as we go through either heating or exposure to different solvents. So we can generally put on the left-hand side hydrocarbons. Aromatic rings are highly stable. And what you'll notice is as we move from left to right, are more oxygen groups, the presence of oxygen groups, and moving those oxygen groups farther out, right? So ethers, that oxygen is somewhat buried. Next comes alcohol, it's exposed. Esters have two oxygens around that enables the electrons to move around and form new bonds. And then aldehydes, generally we can put out here as highly fragile. Um, highly readily attacked. Okay, so we can also think about polarity. Some of these are going to look similar to the stability sets. Um, Here we've got hydrocarbons are nonpolar. All the way on the other side, we have acids. And then we sort of move through the same ether, alcohol, aldehyde trends, right? So more oxygens, more polar. The farther out in the molecule and more exposed those oxygens are, the more polar they tend to be. Okay, so we can put some examples to there. Here we have limonene is going to be very non-polar. Um, Vanillin and rosmarinic acids, which have many oxygens sitting on the outside of the molecule, tend to be highly polar and are going to dissolve in water. We can also say in general that as we sit over here, um, these molecules are going to be more readily volatilized or vaporized, so sent into the gas phase, as compared to these molecules, which are going to not want to vaporize. Okay, so how can we connect this more concretely between structure and extraction technique? We can think of, again, limonene, menthol, rosmarinic acid, and linoleacetate as examples of hydrocarbons, alcohols, acids, and esters. As we go from the top to the bottom, um, we're moving from a non-polar, highly volatile sets to more polar, eventually polar non-volatile, and then volatile but fragile. Because of these differences in the structure, right? Limonene is easy to do and stable with steam distillation. Alcohols like menthol are um, easy to extract either with steam distillation or extractions using many different solvents. Rosmarinic acid, right, is non-polar, or sorry, is highly polar and non-volatile. So we can't use steam distillation, and we want to use a polar solvent to try to pull that out. And then these esters, while they are fragrant and volatile, uh, you know, they're fragile, and so if we were to steam distill them, we're more likely to have them break apart and get off notes in our distillate. Same thing if we expose it to highly active solvents, such as water. This the water may end up breaking down those ester functional groups and changing the underlying structure, and therefore the the way that we're going to experience those compounds. All right. So my takeaway question for you is just looking at the structure of limonene and carval. Um, which solvent would you suggest using to extract them if we're going to do a solvent-based extraction technique? All right. So by the end of today, you should have a good understanding of how we can name plant molecules and how they behave. I don't want you to memorize everything, but you should know, alls mean, excuse me, alls mean alcohol. What a terpene and a terpenoid are, um, because this will just help you do there. So you should feel comfortable with named plant molecules and how they behave in terms of polarity, um, volatiliz volatility, and what this means for extraction. Right. So you should be able to see how we can depict organic molecules, how we name the categories of molecules that are interest to us, and which of these are fragile. All right. So now that we have a basic understanding of these molecules, next time we'll talk about how we can measure and quantify and think about how much of a change happens as we're moving either from the liquid to the gas phase or some reaction is happening. All right. Have a great day.